All set. Hi, everybody. Last day of class. Yeah, I've really enjoyed this semester. We've covered a ton of stuff, as you might have noticed. So today we're just doing section 5.5 again, the substitution rule. A couple of reminders about things next week. I'll be posting information about the exam on the website probably today. It might be tomorrow. We have a quiz today, and you can pick up your graded quiz from the boxes in front of my office, which is room 521. You can always get that information from the Canvas page or from my web page, so you can get your graded quiz 9s starting on Monday there. Our final is Thursday, this coming Thursday, the 11th. And it's 7 p.m., not in this room. It'll be down the hall in Morton 201. I'll send you a reminder of all this stuff by email. If you have exam accommodations, that exam takes place here in this room at 6 p.m. And you need to make sure that you have given me your accommodations letter. So you can't just show up on Thursday and say, actually, I've never told you this, but I have an accommodation. I'm here to take my exam. You know, there's a process for accommodations. We follow the rules, and you have to give us your letter that shows you have an accommodation. So most of you, I think you've all done that. I know that you don't get to take an exam in the testing center without giving them your accommodations. But you know, for you here for this exam, if you have accommodations, you need to make sure that at some point you've sent me your letter. All right. Well, the first thing I want to talk about, meeting part 1. So, as I mentioned, if you were not here on Wednesday, pick up a copy of the worksheet in back. And some of you have graded quizzes that you've not picked up. Okay, so on Wednesday we were discussing the worksheet for the substitution rule, and it should appear here miraculously. Here we go. Substitution rule for finding indefinite integrals where the integrand involves a nested function. And so it was these 5 steps. And then I didn't discuss the method too much. I just started doing a couple of examples. So I did an example, and then I turned you all loose on these 3 particular examples. Remember that this example, this is an integrand involving a nested function. You apply the substitution rule to this one, it doesn't work. There's no, and that brought me to that topic that this famous integral, or this famous function, e to the minus x squared, does not have an antiderivative that can be written as a normal function. You can always write an area function, that functions as an antiderivative, but the substitution method doesn't work, because when it does work, it gives you an honest function. So it didn't work for that one. But we had these 2 examples that did work, example 1 and example 2. I'm going to summarize those over on the side. For that first example, the indefinite integral of e to the kx we found was 1 over k e to the kx plus c. A particular antiderivative would just be 1 over k e to the kx. The general antiderivative, which is what this symbol stands for, has the plus c on it. Now remember that we actually found this just by using the guess and check method. When we first learned about antiderivatives, we sort of figured out this is what the general antiderivative had to look like. But then on Wednesday we saw that you could actually get to that same result using the substitution method, substitution rule. Same thing for this one. We actually studied this one when we did the guess and check method. We found that I think The indefinite integral of that is negative 1/2 e to the minus x squared plus c. Again, a particular antiderivative would be just that part. Put this stuff on to make the general antiderivative. All right, well, that's meeting part 1. Meeting part 2 is definite integrals involving substitution. So, the textbook presents 2 methods. And they actually give examples of where they use both types. So method 1 involves no new rules. So the only things that we do are things that we already know how to do. Method 2 introduces a new rule that's the substitution rule for definite integrals. So, a new rule. So, I'm not a fan of new rules when we already have rules that work. They're you know, I mean, if you just want to think about practically, you know, I paid a lot of money for my substitution rule tattoo. I don't want to get another tattoo that's a substitution rule for definite integrals. You know, if we've got rules that work, you'll be better off learning those rules better by using them in more situations and realizing how powerful they are, than the approach where you feel like, oh geez, every situation has to have a rule. If you don't need a rule. But I will present the book's rule and I'll discuss it, and then I'll discuss again why I don't like it. So example 1. Find the definite integral from 1 to 2 of 1 over 3 minus 5x quantity squared. All right, here we go. So I'm using method 1, no new rules. This is worth a smiley face. No new rules. So as I always do when I'm asked to compute something, I start by writing down the left side so I know what it is that I'm working on. So we've been asked for that. So there's our symbol. I'm going to write that down. Now, I've mentioned this before. This is a very common way for books to typeset this. These these numbers, the book refers to as the limits of the integration. I prefer to just call them the endpoints. We're integrating this function on an interval, and these are the endpoints. And I think it's worth reminding us that these numbers are x values that are the endpoints of the integral. So, this is what's typeset in the book. This is how I would write it. Furthermore, I think there's actually a more concise, more helpful thing that we could put here as an even better left-hand side. What would that be? What symbol would go here?
Would it be the line denoting? I don't know what it's called, but it's the line with the two numbers putting endpoints. So you do.
That's where we're heading.
Okay.
But yeah. Say again? Sigma was a symbol that we used when we were thinking about the day where we ended the day by having a symbol that looked like this. And that was kind of in the middle of that day. You had your hand up? Great. I'm so glad that was your answer, because it's not the right answer, but I'm glad that you answered that, because are you thinking of, first of all, capital F or small f?
Small f.
Okay. Well, so remember that, here we usually use the symbol little f of x for the integrand. So this is what I would call little f. An antiderivative of that we would call capital F, but that's not what goes here either. Because capital F of x that's a symbol for an antiderivative. That's a function. This baby is not a function. It's a number. Signed area. Wonderful. So this is, we're 6 days from the final. I wanted to talk about sort of general stuff like this, remind you of what these symbols mean. When you compute a definite integral, you're computing a signed area. It's the signed area between the graph of this function and the x-axis on the interval x equals 1 to x equals 2. So that's a nice, a much more concise way to write it. So then we can use the fundamental theorem of calculus, part 2, or what's called the evaluation theorem, to say that to do this, we can do this. We find the indefinite integral, and then we evaluate from x equals 1 to x equals 2. Now, I'm going to erase, I think I can fit this in over here. So here we go. We break out, we put way over to the side so we don't interrupt the flow. We put the indefinite integral details. So the indefinite integral is 1 over 3 minus 5x, quantity squared, dx. Now remember on Wednesday when we were doing that worksheet, I talked about different ways of presenting substitution integrals. Let's do this in a very concise way. What happens in step 1?
Find u and t.
Yeah, so what is u? Cooper, what is u?
Inner function.
Yeah, so somebody else, what is the inner function? 3 minus 5x. So in these first two steps, we're trying to find new versions of parts of this integral. So that circled equation is going to give us a new version of that thing. So that's why in this step and in the next step, we want to have equations because we're going to use those to substitute. So step 2, we are going to try to find a new version of the dx. So that's the thing we're after. So we want to have an equation that says dx equals something. It's got to be an equation. So dx equals, well, it's 1 over u prime du. So u prime, if that's u, what is u prime?
-5.
Yeah. So there's my green circled equation. That's going to allow me to get a new version of that green circled thing. So then step 3 is to sub, cancel, and simplify. So I'm doing all that in this one single equal sign. I'm going to replace the 1 over 3 minus 5x squared with 1 over u squared. So I used that red substitution, that red circled equation, to replace that stuff with just u. And then I'm going to use the green circled equation to replace the dx with minus 1 over 5 du. So there I used the green circled equation. So that's the sub part, but now we have to keep going. We have to cancel. Is there anything to cancel here? No, there's not. That's absolutely right. There's nothing to cancel here. But is there something that we can simplify? Yes, there is. What? Yeah.
You take the negative 1/5 out.
Yeah, great. Simplify. So notice this is all still part of step 3, sub, cancel, simplify. Now remember, I'm kind of a stickler about this. The result of step 3 should be a clean basic integral involving just u, no x's. Okay, I've got an integral involving just u, no x's, good. Is it a basic integral? What do I mean by basic integral? I mean, is there a rule that we can just use on this right away? No funny stuff. Like what rule would we use? Cooper?
We can change the 1 over u squared to u to the negative 2.
Yeah, in other words, we're not done here. We're not done simplifying. So minus 1/5 times the integral of u to the minus 2. That's the basic integral because one of our rules applies directly to this. It's a power function with n equals minus 2, so we use the power rule. So step 5, or step 4, what happens in step 4? Wait, say it again?
And that's the proving between u to the negative 2 by ln of absolute value of u.
No, we're going to use just the power rule, and it's the power rule for antiderivatives. So step 4 is the integration step. That was really the thing I was looking for. It was to integrate, and here we have power function with n equals minus 2, and so I'm just going to have minus 1/5 times u to the minus 2 plus 1 divided by minus 2 plus 1. So that's the power rule using n equals negative 2. And then I get the plus c also. So this is, I got to keep simplifying, this is minus 1/5 times u to the minus 1 over minus 1 plus c. The minus 1s have a minus 1 party, and that ends up being u to the minus 1 over 5 plus c. Are we done? Yeah.
You would move the u to the minus 1 to the denominator.
Exactly. So this is still simplifying. 1 over 5u plus c. Are we done? No, because we enumerated our steps. Step 1, step 2, step 3, step 4, and we all know, because we've done this a few times, that there are 5 steps. Oh, so we're not done. What's the 5th step? Yeah, substitute back. So 1 over 5 times 3 minus 5x plus c. So if we wanted to, we could call this our capital F of x. So all of this goes on off screen. The indefinite integral details. Happens that when we got here, we realized, oh, we're going to need to use substitution for this indefinite integral. But that's not a new rule. We already had that rule. It's the substitution rule for indefinite integrals. And again, the way we got here was the way that we were already doing definite integrals. There was no new thing there either. So I'm going to bring that result back, just as we always did, and put that back in those parentheses. And that indefinite integral result goes right in there. So 1 over 5, 3 minus 5x plus c. So now we have to evaluate this at 2 and evaluate it at 1 and subtract. So there I've evaluated it at 2. That is, I just plugged in x equals 2. And then I have to do the same thing at x equals 1. Now, the plus c and the minus c have a c party. So there's a plus c there, and there's a minus c here, so these cancel. And what I end up with is 1 over 5, let's see. Well, let's just do this in our heads. 5 times 2 is 10. 3 minus 10 is negative 7. 5 times negative 7 is 35. So this is minus 1 over 35. Minus, so then over here I've got 3 minus 5 is negative 2. 5 times negative 2 is negative 10. So this is minus 1 over 10. So I need to get a common denominator. This is the lowest common denominator is 70. So this is minus 2 over 70 plus 7 over 70. So that's 5 over 70. So 1 over 14. And that's our answer. Now remember, the evaluation theorem can be written 2 ways. One is you use the indefinite integral symbol here, and you evaluate the indefinite integral from 1 to 2. And so when you do it that way, the indefinite integral brings along with it the plus c. But the plus c gets killed anyway. There's another way of writing the evaluation theorem where you just choose any old particular antiderivative. And then you would have the same calculation but without the plus c. Because for instance, that's a particular if I think about this, that's the general antiderivative, but that would be a particular antiderivative. If I just use that particular antiderivative, I would do this calculation without the plus c. It doesn't matter because the plus c just gets killed anyway. So there's the answer. So notice, it's a fair bit of chalk or ink or pencil, but there's nothing new here. We did what we always have done, for the 3 days that we've been doing definite integrals. For setting up a definite integral, come over here and do the indefinite integral off to the side. It turns out that it needs substitution, so we do substitution, but it doesn't matter. That stays over here, and we come back and put this here and finish the definite integral. Now, let me show you the book's solution. So this was method 1, no new rules. The book does this same problem using the new rule, and I want to show you how that looks. So first of all, there it is. There's the new rule. It's a special rule, substitution rule for definite integrals. So you got to go back to the tattoo parlor, get that thing tattooed on some piece of real estate, and then now when you get a problem, you're faced with, okay, which rule do I need to use? I don't like the idea that every time we do something new, we have to have a new rule. It'd be great if we could learn, how to apply our existing rules to new situations, like what we just did. But they have this new rule that involves, basically you turn the definite integral involving x into a definite integral involving u. But it's a simpler definite integral. So let me show you how that works for the problem that we just did. So here's the definite integral. Here we go. Now, as I said before, I don't like this notation. I would like this to say x equals 1 and x equals 2 to remind us that these endpoints have to do with values of x. Well, part of the method, if you go back up to their presentation of this rule, is they change the endpoints from these numbers which are about x. These are x values, to these numbers, which they don't say it, but these are u values. So I don't like it they don't say it. So let's go see how that looks. So one endpoint was x equals 1. So when x is 1, u turns out to be the number 2. So the new endpoint is u equals minus 2. The other endpoint was x equals 2. Well, when x equals 2, u equals minus 7. So the new other endpoint is u equals minus 7. So we get a new integral with new endpoints. Instead of 1 and 2, we have endpoints negative 2 and 7. Negative 2 and negative 7. But again, I don't like this presentation because a key thing here is we're changing from the world of x to the world of u. So you need to write down a reminder to yourself in the reader. These are values of x. So x equals 1, x equals 2. These are values of u. U equals minus 2, u equals minus 7. Trust me, if you're going to use this method, you should do that. You should label the new values as values of u. According to math people say, well, you don't need to. This tells you that those values are values of x. This tells you that those are values of u. You're just learning this stuff, so you need to remind yourself. These are values of u. And then look, this is a more basic integral that doesn't require the substitution method, but there was some substitution going on because you had to replace that with u. You had to replace this with negative 1/5 du. So there was some so part of the old substitution method shows up in this new substitution method And then look, you get the same number. So that's the method that the book says that they use, and they say, how do they say it? Another method, which is usually preferable, is to use method 2. I don't know why they think it's preferable. I don't think it's preferable. If you're a darn fool, you can use method 2. But as I've said before, you can use a valid method. If you learned method 2 in high school and you prefer using method 2, great. But as I said before, you need to be able to present stuff in a way that's mathematically clear and correct. My examples, I'm always going to use method 1. Okay. Okay, example 2. Find the example 2. Bacteria population starts with 100 bacteria and grows at a rate R of t equals 200 e to the 200 e to the 5t over 4 bacteria per hour. So this is a winter break problem. This is what happens, when you leave your apartment for winter break and you leave some stuff on the kitchen counter. What happens during winter break? What's the bacteria population at time t equals 7 hours? Okay. Well, let's let P of t be the population at time t. So then what we're being asked for is capital P of 7. Okay, well, I'm going to start by doing something that's going to seem really silly. P of 7 equals P of 7. Everybody okay with that? Now, how about this? P of 7 equals P of 7 minus P of 0 plus P of 0. Okay, I didn't do anything. I subtracted something and added it right back. Well, this is common. This is a trick. The reason I do this trick is because I want to introduce something that I can deal with. This thing, P of 7 minus P of 0, another name for that is delta P. So the new population is whatever the original population was plus the amount the population changed. Now I'm going to turn this around so that I have P0 on the left. Just like having P0 first. So the new population is whatever the original population is, plus however much the population changed. Okay, well, that's P0 plus the integral from t equals 0 to t equals 7 of P prime of t. This is using the net change theorem. You want to know how much a quantity changes, you integrate its derivative. Oh, well, let's go back over here. If P of t is the population, then this thing they gave us, R, a better name for that would be P prime. So P prime of t would be R of t, which would be 200 e to the 5t over 4. So that's what's going to go in here. So P of 0 is 100 plus the integral from t equals 0 to t equals 7 of P prime, that thing, 200 e to the 5t over 4. Well, I'm going to pull that 200 out. So 100 plus 200 times this integral, t equals 0 to t equals 7 of e to the 5t over 4. Here, we've got one of these babies. This is the integral that we did on Wednesday using substitution. So I'm just going to pull that result. So this is using Wednesday's result. Oh, what I need to do, sorry, I need to do 100 plus 200 times the indefinite integral of e to the 5t over 4, evaluated from t equals 0 to t equals 7. So here, I pull in that result. So 100 plus 200 times that thing. 1 over 5 over 4, e to the 5t over 4, evaluated from t equals 0 to t equals 7. So this is using Wednesday's result. But if we didn't have that result from Wednesday, here we would break off, and on the sideboard we'd do the indefinite integral, which would involve substitution. We'd bring the result back, and that's where we'd go. And then from here on out, it's just arithmetic. All right, so again, the thing about definite integrals involving substitution is that there's nothing new. You're using the regular techniques in the way that I like to do it. You just use the regular approach for finding a definite integral, and you use the regular substitution technique for finding the indefinite integral. All right, let's do our quiz. That was a lot of content this semester. Thank you all so much. It's been a pleasure teaching you all. Oh, I didn't pass around